Hello everyone, welcome to a new video. This video is about the nonlinear effects in an optical fiber. So there are certain nonlinear effects in optical fiber which critically degrade the performance of optical fiber communication networks. So let us get started. There are mainly 5 types of nonlinear effects in optical fiber, and they can be broadly classified into 2 types depending on how they are occurring. Okay, so the first type is due to the non-linear inelastic scattering processes happening in the optical fiber. And due to those scattering processes, there can be 2 types of non-linear effects. One is the stimulated Raman scattering and the other is the stimulated Brillouin scattering. Okay. Now the second type is due to the variation of the refractive index of the fiber depending on the intensity of the optical signal. And like we study, the refractive index of the optical fiber is not a constant in a practical network. It varies depending on the optical intensity, and that gives rise to nonlinear effects in the optical fiber. And this nonlinearity is known as the Kerr nonlinearity, and due to Kerr nonlinearity there can be 3 effects. They are self-phase modulation, cross-phase modulation and 4-wave mixing. So these are the 5 types of nonlinearities in optical fiber. We'll discuss each of this in detail. So first let us discuss the stimulated Raman scattering, abbreviated as the SRS. And SRS is caused due to the interaction between the light wave and the vibrational modes of the silica molecules. And due to this interaction, the incident photons get scattered and they attain a lower frequency. That is, the energy of the incident photon is reduced. You know that as you reduce the frequency, the power given by h nu is reduced. And the scattered photon is then called as the Stokes photon. Okay, the scattered photon or the Stokes photon is typically traveling in the same direction as that of the incident beam. Though the scattering can happen in any direction, it is predominantly happening in the same direction. So the scattered wave will travel in the same direction as that of the incident wave. The incident wave is also called the pump wave or the pump beam because the source of energy is the incident beam, and that is known as the pump beam. And the scattered beam is known as the Stokes beam. Okay. SRS can exist at all incident power levels, but it is significant in communication systems where the power exceeds a particular threshold. Now the expression for threshold power for the SRS is given as PTH is equal to 16 into A effective, that is the effective core area, divided by GR into L effective, where L effective is the effective length of the fiber and GR is the Raman gain coefficient, which is characteristics of the particular material used in the fiber. That means the threshold power increases as the effective area of the core increases, while the length of the fiber is inversely proportional to the threshold power level for SRS. That means as the length of the fiber increases, even for very low values of power, the effect of SRS will be predominant. Okay. So whenever the incident power is greater than this threshold value, there will be the effect of SRS in the communication system, and it can critically affect the communication. Okay. So consider a multi-channel system where there are multiple wavelengths. In that case, the energy of one wavelength can be transferred to a longer wavelength due to this effect. This shift in wavelength is known as the Stokes shift, and the same is illustrated in the diagram as you can see. And the input power levels were all same for different wavelength, but as they pass through the optical fiber at the output, you can observe that the longer wavelength is having the higher power and the power of the shorter wavelengths are reduced due to this scattering. Though this is a limitation for most of the communication system, this kind of scattering is made use in other applications like the Raman amplifier and all, where a pump source is used to amplify the signal using the Raman scattering. So that's all about the Raman scattering. Now the next type of nonlinear scattering loss in fiber is the stimulated Brillouin scattering, also known as the SBS. And these both scatterings SRS and SBS are nonlinear scattering losses and also inelastic scattering loss. Nonlinear because it is highly dependent on the input power level. But in the case of linear scattering loss, it is mainly due to the properties of the material. Here it is highly dependent on the input power level. Also it is called inelastic because there is frequency shift. So how does this SBS happen? SBS rises when light wave scatters from an acoustic wave. It happens when the light is incident on the acoustic waves in the optical fiber. So how is this acoustic waves produced? The incident waves cause tiny density variations in the fiber, resulting in acoustic phonons. So when light wave is incident on these acoustic phonons, that causes a backscattering of the incident light. So unlike SRS, here the scattered direction is mainly in the backward direction. So the signal power is partially transferred to the backward light and thereby reducing the propagating signal power. Okay. So when the light is scattered back, it experiences a Doppler shift in frequency, which can be given as nu b is equal to 2 into n into Vs divided by lambda, where Vs is the velocity of sound in the material. Nu b is the frequency shift and or the Doppler frequency, and lambda is the wavelength, n is the refractive index. So this shift in frequency, the frequency is actually reduced when it's backscattered. So that shift in frequency is usually about 10 gigahertz or so. For 150 nanometer propagation in fused silica fiber, the shift in frequency is about 11 gigahertz. So since the shift is very less, we can say that the effect is confined within a single channel, even though it is a multi-channel system. Even though this happens in a multi-channel system like a WDM, the effect is not affecting the neighboring channel. The effect is confined within individual channels because the shift is very less compared to the channel spacing. Okay. So here also the effect becomes significant after the threshold power, and the threshold power can be given as 21 into effective area of the core divided by GB into L effective, where L effective is the length of the fiber and GB is the Brillouin gain coefficient. So the SBS threshold power is usually always above the SRS threshold power level, and PTH is defined as the power at which the power of the backscattered light will be equal to the fiber input power. So SRS and SBS are the two inelastic scattering losses, non-linear scattering losses happening in the optical fiber. So we have discussed about the nonlinear effects due to scattering in fiber. Now we are going to see the nonlinear effects due to the intensity dependent variation of refractive index of the fiber. There are three types: self-phase modulation, cross-phase modulation and four-way mixing. First, let us see what is self-phase modulation. So the refractive index of most of the optical materials is not actually a constant, but it has a weak dependence on the optical intensity. Okay, so depending on the intensity of the signal propagating, there will be slight variation for the refractive index of the material. So the expression for refractive index can be given by n is equal to n0 plus n2 into I, where n0 is the ordinary refractive index, n2 is the non-linear index coefficient which represents the variation, and I is the intensity of the optical signal. Okay. So this non-linearity in the refractive index is called Kerr non-linearity. And due to this variation in refractive index, what happens is that there is a phase modulation happening to the signal. Due to the intensity fluctuation, the refractive index will fluctuate accordingly, and therefore the phase of the signal will also fluctuate. That is why it is called self-phase modulation. The non-linearity of the refractive index due to the intensity variation will cause a phase modulation in the same wave. That's why it is called self-phase modulation, and it is also called the Kerr effect. That is the non-linearity that results in the phase modulation of the propagating signal. Okay, so that is what's shown in the image. As the intensity of the optical signal pulse increases, there will be a variation for the refractive index, and therefore there will be a phase change happening. And we know that the rate of change of phase is the angular frequency. The expression for frequency can be given by, not angular frequencies, normal frequency can be given by f is equal to 1 by 2 pi into derivative of, or the rate of change of phase. Okay. So thus, due to the intensity fluctuation, there will be refractive index variation. Due to that, there will be phase variation. And the phase variation means there is variation in the instantaneous frequency of the signal within the same pulse. Okay, this is known as frequency chirping, slight frequency variation for the instantaneous frequency. That is called the frequency chirping. That means we will be loading an input signal at a particular frequency, but throughout propagation that is not maintained. There will be slight variation due to this non-linearity. Okay, so thus the intensity variation causes refractive index variation, and that causes phase modulation and results in frequency chirping and the spectral broadening of the pulse. This effect is called the self-phase modulation. Self-phase modulation is mainly confined about the same wave. It is not about multi-channel interference or anything. It is confined within the same propagating signal. Okay. Now the next is cross-phase modulation. This is the same like self-phase modulation. The only thing is that this is happening in multi-channel system like WDM systems, and the reason is also the same. That is Kerr nonlinearity is the reason for cross-phase modulation. That is the variation of refractive index with power fluctuation in the signal. But here what happens is that the power fluctuation in a particular wavelength channel is causing phase modulation on another channel. In self-phase modulation, the phase modulation was on the same signal, but here due to the power fluctuation in a particular channel, the refractive index of the fiber gets modified slightly. It varies depending on the power fluctuation, and that causes phase modulation on a co-propagating another signal at a different wavelength. That is why it is called cross-phase modulation. One channel is affecting phase modulation, is causing phase modulation on another channel. So this is also same like self-phase modulation. The change in power fluctuation causes nonlinearity in the refractive index. That causes phase modulation on another wavelength and thereby frequency chirping in the next channel. Okay, so that's all about cross-phase modulation. Now the next nonlinear effect is four-wave mixing. This is also a result of Kerr nonlinearity, and four-wave mixing is a third order nonlinearity in silica fiber. Because when you expand the expression for nonlinear polarization with respect to electric field, the even order terms get cancelled out because of the centrosymmetric properties of silica fiber. That is, the fiber is symmetric through the center. Due to this reason, the second order power get cancelled out, and the third order power remains. So due to this third order power, there will be cross product terms between different frequencies, and thereby new sum and different frequencies are generated. Okay, so when this new frequencies falls in the transmission window of the original frequency, what happens is that causes severe crosstalk. As you can see in the expression, suppose we have frequencies like nu I, nu j and nu k. These are the original signals supposed to propagate through the fiber in a WDM system. In that case, what happens is that the third order nonlinear polarization causes sum and product terms, and consider that the most significant term is nu I plus nu j minus nu k. This is mostly the predominant crosstalk caused in four-way mixing. Okay, so as you can see, three frequencies are mixing together to form a new frequency. That is called four-way mixing. Okay, and this new frequency will grow at the expense of the original signal power. That means our original signal get depleted while propagation, and at the same time a new frequency within the transmission window is growing in strength. So that causes a fake channel at the receiver. The original channel will die out, and at the same time the power from the original channel is taken by this new frequency generated. So here the important points are, this is the third order nonlinearity effect, and there is a new fake channel created in four-way mixing. Unlike in cross phase modulation and self phase modulation, there is no fake channel, but here there is a fake channel produced, and that grows in strength at the expense of the original signal power. Okay, so that's all about four-way mixing.